last few videos we were looking at the linear regression thing, that how we can perform linear regression. So in today's video we'll be looking at how we can perform a polynomial regression. So let us work on polynomial regression. So this is the thing we'll be looking at, which is polynomial regression, right? So let us start it. So what kind of, you see, we'll see that polynomial regression is way more complex as compared to linear regression. So but for specific cases we can do the hand calculations, but most of the time we have to rely on the computer codes, because hand calculations are not useful when you are doing, data analysis, when you have big data. But still, for the understanding, for you to know that what the method exactly is, you should know the mathematics and you should know how you can do it right step by step. So that is the aim of the video, that we are going to look at polynomial regression. And then this course is a combination of mathematical videos, as well as we are making videos on the programs, writing programs in Python. So there is a combination, so you don't have to be worried. You are learning both the theoretical aspect as well as the implementation aspect. So now let us start with polynomial regression. So what I will assume here, that my data looks like this. Suppose I have only one feature. Let me call that feature as x. And then suppose I have only one output. Let me call it as y, right? So there is only one feature and one output, which I am calling as x and y, right? Okay, so what will happen, you have xi values here, okay, some values of x and the corresponding values of y. And what you are interested in, you want to write y as a polynomial function of x. So let us take, for the simplicity, that we are taking a second order polynomial, theta naught x, theta naught plus theta 1 x plus theta 2 x square, right? So this is the polynomial I'm interested in fitting here. So we'll follow the same approach which we had followed in case of linear regression. So what you will be doing, you will be saying that suppose this is my, this here is my polynomial which I am trying to fit here. Then my aim is to find out these theta naught, theta 1 and theta 2 parameters on the basis of the data set which I have here. So what you have to do here, you have to start from, you will write your error function, right? So what was our error function? Error function was, you have to write your yi is your exact value for each instance, and then for that yi, this is what you are predicting, theta naught plus theta 1 x I plus theta 2 xi square, right? Okay, so what you can do is, this is the error for one instance, and I will take the square for the reasons which we already know, that because we don't care, whether it is a negative error or positive error. We want to minimize the error, so we'll sum it over all the instances. Let us say there are total n instances, right? And for making mathematics simple, we have to divide with the 2, right? So that is the idea of you know uh, uh, error term, right? An error term. Now we have this error term, right? This is the error term you have. Okay, so what we are going to do with this error term, we will try to find out the values of theta naught, theta 1 and theta 2 in such a manner that the error is minimized, right? So now the next thing is, find the values of, find the values of theta naught, theta 1 and theta 2 in such a manner that the error is minimized, the error is minimized, right? So this board I am using for the first time, this is a fig jam board, so it's not going down. Yeah, it's going down now. Okay, yeah, we are good. Okay, now how we can minimize the error? For minimizing the error, what we have to do, we have to differentiate it with respect to different parameters. Let me call it as j. So I have to differentiate it with respect to theta naught, and differentiate it with respect to theta 1, and differentiate it with respect to theta 2, and put it equal to 0. So that is what we have to do. Now here if you look what is the derivative with respect to theta naught. So you see this is the term theta naught. So we are going to use the chain rule, right? And then we will be differentiating. So let me write down the derivative with respect to theta naught. So curly j by curly theta naught is going to be, this 2 will come in the front. So you have 1 by 2 summation I from 1 to n, 2 times you have yi minus theta naught plus theta 1 xi plus theta 2 xi square. And then because you have to use the chain rule, the derivative with respect to theta naught is 1. You put it equal to 0. Then you do the derivative with respect to theta 1. So that will be same. 1 by 2 is already in the front. The power 2 will come in the front. So you have yi minus theta naught plus theta 1 xi plus theta 2 xi square. And then you have to differentiate with respect to a theta 1, right? So you will get xi. So we'll write it as xi equal to 0 because derivative with respect to theta 1 will be this term xi, right? So I hope that makes sense. Okay, so now we have to do the next derivative with respect to theta 2. So you can see that there is a term theta 2 is associated with xi square. So that term will come here when we will be using chain rule. So when I am differentiating with respect to theta 2, so I'll get I from 1 to n. This will be I from 1 to n. It's not writing. Okay, so this is I from 1 to n. 2 will come in the front. So you have yi minus theta naught plus theta 1 xi plus theta 2 xi square. And then xi square will come here and this is equal to 0. Right? Okay, so you see this board I am using for the first time. So there are so many glitches, but that's okay, I think. I like the, there are so many nice features here, the kind of pens you can use, kind of stickers, like we have a sticker like this. So I like this platform, but okay, we'll learn it how to use it, no problem. Now let us work here. What we will get if we try to simplify, this 2 cancels everywhere, right? Okay, so we'll do one at a time. I am interested in calculating these theta naught, theta 1 and theta 2. Everything else I know. So let me write down. I'll bring theta naught, theta 1 and theta 2 on the left hand side and then all other terms on the right hand side. If you do it here, so what it will be? It will be theta naught, and then because this is a summation, so summation I from 1 to n, right? 1 to n, then you have xi, and then you have, for the second term, theta 1 will come out, and because you have uh, okay, this was not xi, this was 1, right? This is 1, and for the second term it is xi, I from 1 to n, and for the third term it is xi square, I from 1 to n, and this term yi will move on to the right hand side, I from 1 to n. So this will happen, this is what will happen to the first equation. Now let us look at the second equation. So here you see you have xi multiplied. So theta naught will be along with xi. So you have I from 1 to n xi, and then you have this theta 1 term, and then you have xi square. So I xi square, I from 1 to n, and then you have this term theta 2, and then along with theta 2 you have xi cube, right? Xi cube, and on the right hand side you will have this term yi and xi, so you have a multiplication of xi and yi, I from 1 to n. Now let us look at the third term. You look at the third term. Here again you will get theta naught. Here you have xi square, theta naught multiplied with xi square. So I from 1 to n xi square. Then you have theta 1, and that is with xi cube. So you have I from 1 to n xi cube, and then you have theta 2, and then you have xi raised to power 4, and that is equal to yi into xi square, yi into xi square, I from 1 to n. So now you see you have a nice system of equations here. These are your unknown parameters, theta naught, theta 1 here, and theta 2 here, and everything else is known. So we have a plain simple system of equations which we can solve. So you can write it like this. Let me write down it in the matrix form because that is our favorite form, matrix form. So when you write it in the matrix form, you see, okay, it's your choice how you want to write it, right? So if I write theta naught here, theta 1 here, theta 2 here, then my first equation is xi square, and then this is xi, and this is summation of 1 from 1 to n is going to be n. This term is going to be n. And for the right hand side, this is equal to summation yi. And now I look for the second equation. So these are my coefficients. This is xi cube, xi square, and then you have xi, and then on the right hand side you have xi yi, and then for the third one I have here xi 4, then I have xi cube, then I have xi square, right, and on the right hand side I have xi square yi, right. So this is my system of equation, a system of equation which can be solved. Linear system of equations, right? So we have linear equations here. So here we had only one feature, and we were fitting polynomial of degree 2, polynomial of degree 2, and if you fit a general polynomial of degree, say p, fit a polynomial of degree p, then what will happen if I'm trying to fit a polynomial of degree p, then also you'll get something similar. So you'll get something like this, that you have xi power p here, then you have p minus 1 here till you get a 1 here, and then in the next row you will have, you see, we started here with xi2 because we were fitting a polynomial of degree 2. So we have to recognize the pattern. Here it was 3, here it is 4, right? So here it will be p plus 1, and then you keep on increasing, p plus keep on decreasing, I'm sorry. So it will be p and so on. Here it will be simply xi, and in the next row it will be p plus 2, then here it will be p plus 1 and so on. Here it will be xi square, and in the last row you will have the, this was twice of 2, so this is 2p, and then you have 2p minus 1 and so on, and here you will have p, right? So this is the matrix you will have when you are trying to fit a polynomial of degree p, and then you have here, because you are trying to fit a polynomial of degree p, so you have theta p, theta p minus 1 and so on, theta naught, right? So you can see that this is a polynomial, this was a 3 cross 3 matrix, right, for a polynomial of degree 2. So this should be p plus 1 cross p plus 1 matrix, that you can check, right? Okay, and on the right hand side you will have yi, then you have xi yi, then you have xi square yi, and then you have xi p yi, right? So this is the system which you have to solve, right? So this is the required system of linear equations. Okay, so this is what you have to solve for. So we'll just, but you can see this is a complex system, right? It's not easy to solve, right? To solve this kind of system you have to be like if I want to do it manually, it's a complex job, right? So that's why we want to use the Python codes. And also, suppose I have more than one feature, suppose I have more than one feature, then what will happen, right? So then what will happen, suppose I have this something like this x1 x2 and then you have y, right? In that case I have to try to fit a polynomial of say degree 2 polynomial. Then what kind of polynomial it will look like? Then we have this, because we have to consider x1 and x2, so it will be something like this: a plus bx1 plus cx2 plus dx1 square plus e x1 x2 plus f x2 square. So you can see that this is going to be a complex polynomial, right? So, but we have a polynomial of degree more than when we are more than 1 when we are fitting the polynomials and we are doing the regression problem. Okay. So this means that simply doing the hand calculations is very tough. So we will be relying on the codes for our polynomial fitting, but for just for your understanding, let us just work on one very simple example, numerical example, where we are going to fit a quadratic polynomial. So suppose this is my data x, y. I have only one feature 1, 2, 3, 4, 5, and then I have 1, 14, 19, 16, and 25. And the question is fit a quadratic polynomial, right? Okay, so if we want to fit a quadratic polynomial, so what we can do here is, we know that because we want to fit a quadratic polynomial, so matrix will look like 1, sorry, not 1, it's n is the number of instances, then summation xi square. Here it will be summation xi square, summation xi cube. This is what just we created, xi square, xi cube, and then you have xi power 4, and then here you have theta 2, theta 1, and theta naught. If I am trying to put a polynomial of like this, theta naught plus theta 1 x plus theta 2 x square. So this is the polynomial I am looking for, and then this is equal to summation yi, summation xi summation xi square yi. So now you can see that these are the columns you have to create, right? So you have to create a column for, we already have for xi as well as yi, but for all others, right, xi square, xi cube, xi4. So these are the columns you have to create, and these two, right? So let us just try to create these columns, right? So what I am going to do, I am going to write the data again. So I have my xi and yi, right? So this is 1, 2, 3, 4, 5. Then I have yi 1, 14, 19, 16, and then you have 25. So I want to create xi square, xi cube, and then I want to create xi4, and then you have xi yi, and then you have xi square yi, right? Okay, so what you will be doing, you will do square here, 1, 4, 9, 16, 25. You do the cube here, 1, 8, 27, 64, 125. You do the fourth power here, so this is 1, 16, 81, 256, 625. Then you multiply this xi and yi, you will get 1, 14, xi and yi. If I multiply 28, I'm sorry, 128, then you have 57, right? If I multiply 9 and 19 and 3, then you have 64, then you have 125, and then I multiply this xi square and yi, and then what I am going to get is, you can just see, 156, 171, 256, 625. My aim here is to get you, like, I want you to know that how much work is involved, right? In how many calculations are involved, so you have to appreciate the codes which will be making, right? Okay, now we want the sums. So if you add these columns, you'll get 15 here, 55 here, 225 here, 979 here, 75 here. Oh, I'm sorry, yeah, this is, I'm writing it wrong. Okay, so you'll be getting this yi is 75, and then xi square is 55, xi cube is 225, xi 4 power is 979, and here you get 275, and here you get 1109. So I put all these values here, okay, here. So what you will get, if I put all these values here, your matrix look like 55, 15, 5. Then you have 225, 55, 15. Then you have 979, 225, 55. And then you have your vector of unknowns, theta 2, theta 1, theta naught. And on the right hand side, you have to write yi sum, which is nothing but 75. then you have 275, then you have 1109. Now what I want to do, I want to invert this matrix. So I find A inverse. Let us find A inverse if I call this matrix as A. So that is your task, you have to find out. But once you do this, this is the inverse you are going to get. 1 by 2 minus 3 by 7, 1 by 14 minus 33 by 10, 187 by 10 minus 3 by 7, and then you have 23 by 5, then you have minus 33 by 10, and then you have 1 by 2, right? And then you want to multiply A inverse and B, so that is 1 by 2 minus 3 by 7, 1 by 14 minus 33 by 10, 187 by 10 minus 3 by 7, 23 by 5 minus 33 by 10, 1 by 2. You want to multiply it with the right hand side vector, which is 75, 275, 1109. When you multiply, this is what you'll get, minus 1.1429, 11.8571 minus 8. So that means the polynomial we are fitting here looks like this. Y is equal to minus 8 plus 11.8571x minus 1.1429x squared. So this is the polynomial which is to be fit for this particular data set. Okay, so we will be looking at how we can made a Python code, right? And one last comment which I want to make is that, instead of doing the derivative equal to 0, we want to minimize this particular thing, right? So we can go choose the path of optimization, right? So you can apply gradient descent on this error function, right? This is same as we did in the last case when we were doing the linear regression. So that is another task, and most of the Python codes which we'll be writing, that will not creating the system of equations. Instead we'll be working on the gradient descent method, because that is the practical approach when you are dealing with the numerical data, right? Thank you for watching this video. Please share this video and subscribe to this channel. Thank you. Happy learning.